Yeah, I would like, so I will introduce myself. So I'm Xiaozhe Wang. I'm the assistant professor in the Department of Electrical and Computer Engineering at McGill University. I joined McGill in January 2016, so I have been here for 6 years, actually, almost, yeah. My research interest in power system, stability and security, and also as well as the data-driven monitoring and control in power system, and then certain quantifications in power systems. So I think my research is in line with the scope of the GERAD, like using data and also then certain analysis for and then certainly aware control and decision making. So can I start or can I start my presentation?
Sure.
Okay.
I mean, whenever you're ready, you can start your presentation.
Okay. So so thanks for the opportunity. I'm going to present some of my group's recent works in applying polynomial chaos extension methods in power system probabilistic security assessment. So before I start, I would like to first acknowledge my students, Xiaozhe Wang and Dr. Xiaozhe, who have made great contributions in the work I'm going to present, as well as the founding agencies and supporting partner, Dr. Liu from Power Tech Labs, for all the helpful discussions. So motivation of my work is the continuous integration of renewable energy sources worldwide. So the left figure, we can see that the global wind and solar installations are exponentially growing since 2000. And renewable share of the annual power capacity is also growing year by year. And these trends are going to continue in the near future to mitigate the climate change and to develop sustainable communities and cities. Well, the challenges for integration of renewable energy sources are commonly known because they're subject to weather conditions. So the sun doesn't always shine or the wind doesn't always blow when energy are being needed. So the figure here gives us an idea about the randomness we have in power system on both the load side as well as the renewable generation side. So because of the uncertainty, they may affect the system operation in different aspects. Well, indeed, so 6 years ago, actually in my PhD work, we have carried out a study to investigate uncertainty of renewable energy sources, and it turned out that we showed that uncertainty may alter the stability property of the power grid. So here on the left is the time domain simulation of a power system when we just consider a deterministic model without considering the randomness from the wind and solar. We see that the system is stable. However, on the right, when the wind stochasticities are being incorporated and we run a stochastic model, the system becomes unstable. So this is a very strong argument to say that the uncertainty and randomness needs to be carefully considered in the power system analysis. And this result was also motivation for my subsequent work in the recent years. So generally speaking, the uncertainty impact can be classified into the static security assessment and dynamic stability analysis. So for the sake of time, I will focus on the static security assessment in this talk, while we have also done studying dynamic stability analysis. So for the interested audience, I have also listed a reference here that you can refer to after my talk. Okay, so let's start from the first one. The impacts of uncertainty on available transfer capability, ATC. So what is ATC? It's actually closely related to another concept called total transfer capability, TTC. So TTC refers to the power that can be transferred over a path in a reliable manner. So for example, if we want to transfer power from Quebec to Ontario, we want to make sure that this power transfer can be met without violating stability limit, voltage limit, and thermal limit in both the base case as well as in all the post-contingency cases. Okay, so as you can see that the power system is evolving in time, the TTC has to be assessed periodically, and in the near real-time horizon, it has to be assessed every 15 minutes. So how do we assess ADC and TDC? So in the deterministic framework, okay, so once we get the TDC, the total transfer capability, we subtract it by 3 margins. Okay, EDC is existing transmission commitment. CVM are the capacity benefit margin. So these are something determined by the utility power flow solutions and market models, and are not something we're interested in here. So we just regard them to be constant. While the TRM is the transfer reliability margin, which is reserved to account for all the uncertainty in the system. Okay, and typically is, for example, 5% of the TDC is reserved as a TRM to account for uncertainty. Well, as the uncertainty level is growing because of the integration of renewable energy sources and electric vehicles, we believe that the TDC and ADC need to be assessed in the probabilistic framework. So what does it mean? It means that the TDC is no longer a deterministic value, and rather it's a random variable that exhibits some probability distributions. And the TRM here can be determined from the difference between the mean value of the TDC and, for example, the 5th percentile of the TDC. And as a result, we can get an ADC with 95% confidence level. Okay, so from this figure, it can be seen that the key point to estimate ADC is to get a good estimate about the probability distribution of the TDC, from which we can calculate TRM and then to get the ADC with certain confidence level. So the question is, how do we estimate the distribution of TDC? So there are different ways. We adopt the continuation power flow formulation. So for example, we have a power transfer understanding, which is described by this vector B. And along the direction, we increase the power when we firstly meet the voltage limit and then the thermal limit. Eventually, we may meet the static stability limit. And the minimum between the 3 will give us the TDC for that particular case. And remember that we may have a long contingency list, so we have to do exactly the same thing for all the post-contingency cases. And the minimum among this lambda will give us the TDC for this particular power transfer. Okay, and U here are random variables describing the random wind speed, solar radiations, and low power, line outages, so on and so forth. So as you can see here, for a single scenario of the random inputs, evaluating TDC is rather complicated. Okay, so you have to do this calculate using this formulation for all the contingencies. And you can imagine that it's going to be computationally expensive if we want to estimate a TDC distribution by running Monte Carlo simulations. Okay. Well, so as a result, in the work 3 and 4, we apply the polynomial chaos expansion method. So how does it work? So conventionally, if we run the Monte Carlo simulations, we have one scenario, we feed into the physical model, which is the continuation power flow model described in the last page, and we get a response. And then we can generate a large number of scenarios, feed them into the physical model, get the response, and estimate the TDC distribution by drawing a histogram. While the PTTC method will do it in a different way. Okay, so it will firstly generate a small number of scenarios, and we feed them into the physical model, and we get the response, which is the TDC in our study. And then from the small number of inputs and outputs, we try to build up a surrogate model, which is a pure algebraic model. Okay, and after building up this model, we can generate a large number of scenarios for the random inputs, and we can estimate a TDC histogram by directly substituting all the scenarios to the surrogate model. And that's going to be very fast because the surrogate model is just the algebraic model, is a series of polynomial expansion. So compared to the CPF model, we showing here takes negligible time. So that's the essence of the PTTC method. All right, so then I would like to talk a little bit more details about how to build up the surrogate model. But in case you feel it's too detailed, you can skip these 2 slides and come back after 2 slides. So roughly speaking, to build up the surrogate model, there are 2 steps. Firstly is to find the polynomial basis, and then to calculate the coefficients. Well, to find the polynomial basis, if we know the marginal distribution of the random inputs, for example, if it follows normal distribution, we can use Hermite polynomial. If it is beta distribution, we can use Jacobi polynomial. So it's not hard, okay? And if the distribution, marginal distribution is out of the table, we can still build up the polynomial by applying still-chase procedure. Well, our question here is that what if the marginal distribution of the random inputs is unknown, which may be the case in practical applications, because the marginal distribution may be either inaccurate or unavailable. Rather, the raw data is more likely to be accessible. So this is the wind speed data I got from the NREL, the National Renewable Energy Labs, on their website when I prepared for this talk. So thanks to many joint efforts and initiatives, accessing the raw data is not hard these days. So our question is whether we can apply the PTTC method directly using data instead of firstly inferring the marginal distribution from the data and then applying the PTTC method. Because in that way, we may have inaccuracy introduced in the inferring process. And it turned out yes. So in our work 4 here, we have proposed a data-driven polynomial chaos expansion method by utilizing the condition that polynomial bases have to be orthogonal to each other. So now we can build up the univariate polynomial bases using this relationship from the raw moments of the random inputs. Well, the raw moments can be easily calculated or estimated from the raw data. Okay, and once we have the univariate polynomial and we can build up the multivariate polynomial bases, and the last step is to find a coefficient, we can either apply simple regression method or more advanced bar scheme like the least angle regression method we adopted in this work to find the coefficients. All right, so this is how we build up the surrogate model, and after that we can generate a large number of scenarios for the, or directly using the data obtained from the website or from the real wind farm. And then we can substitute those data to the surrogate model to estimate the TTC and then to draw the histogram. All right, so I would like to show some results in our numerical study. So it is done in a modified IEEE 118 bus system where we have 111 random variables coming from 6 wind farms, 6 PVs, solar farms, and 99 loads. The contingency list and the power transaction study, study are also presented here. And the total transfer capability assessment is done using a commercial power system analysis tool, which is called the DSA tool. All right, so firstly, we validate the accuracy of the PTTC method. So it can be shown here that both the data-driven sparse PTTC and the sparse PTTC can provide very accurate estimation for the PDF, the probability density functions, and the cumulative distribution function CDF for the TTC, as well as the statistics. So here I only show the PDF and CDF. And in terms of the computational efficiency, so the PTTC methods require 556 simulations to get the inputs and outputs. And once we get the inputs and outputs, building up the surrogate model and the sample evaluation just take negligible time. While in contrast, the Monte Carlo simulations take like 10,000 simulations to have converged statistics. So here in this case, we see that the PTTC method is approximately 18 times faster than the Monte Carlo simulations. And regarding the impact of uncertainty on the ADC, so in the deterministic framework, we just have a deterministic TTC from the CPF model, which 139 megawatts. And if we reserve 5% of TTC to be the TRM, which is around 7 megawatts, the resulting ADC is 132 megawatts. However, in the probabilistic framework, the mean value of the TTC is 140 megawatts. And then we can calculate TRM by the difference between the mean value of the TTC and the fixed percentile of TTC. And it turned out to be 49 megawatts, and the resulting ADC is 90 megawatts. So here we see that because of the randomness and uncertainty in the power system, the available transfer capability has to be reduced by more than 31%. Okay, so this is like, you know, the impacts of uncertainty on ADC, which is quite significant. So in the paper, we also have similar observations for different scenarios where we have considered line outages. So we model the line outages as discrete random variables following Bernoulli distribution. We have also considered a -2 contingencies, and we have included the underload tap changer transformer in the TTC assessment. So in all the different cases, we have similar observations. All right, so a brief summary about the TTC method. So firstly, it has a very sound mathematical basis that the polynomial expansion is going to converge to the true model response in the sense of L2 norm as the order of the polynomial goes to infinity. And also it can be easily integrated with any deterministic analysis tool. So in our case, we just combine it with a commercial power system analysis tool without, you know, we have going to the underlying codes of the two. So they can be integrated seamlessly. And with advanced bar scheme, now we see that the TTC method can provide accurate estimation for the probabilistic characteristics of the TTC very efficiently. And regarding the data-driven TTC methods, it has some additional advantages. So firstly, it doesn't require any pre-assumed probability distributions for the random inputs. We can build up the polynomial basis directly from data, and it is applicable to both continuous and discrete random variables. And inside, so in our study, we have seen that because of the uncertainty that there is a significant reduction of the available transfer capability, and PCE methods, no matter whether it is conventional sparse PCE or data-driven sparse PCE, are good candidates to assess the ADC and TTC in the probabilistic framework. Regarding the future work, so now we have seen that uncertainty may have a negative impact on the power system operation. So next question is, how can we mitigate this negative impact? So what we're considering now is to pinpoint some critical random variables such that we can better shape the probability distribution of the model response by smoothing out just a few random variables. And in that sense, we can enlarge the ADC with a certain confidence level significantly. Okay, so by using the, so we are exploring the global sensitivity analysis in that in this study. And this is something ongoing we're currently working on, which we believe are, you know, important and also interesting. All right, so in our study, we have realized that the PCE method is an effective method to quantify the uncertainty propagation from the random inputs to the model response, and it can be applied in different applications by having different physical models. For example, in our study, the TTC physical model is the continuation power flow model, but it can also be applied to study probabilistic power flow, economic dispatch problem, as well as instability and risk analysis. So the topics marked in red are something we have been exploring, and we believe it can also be extended to study other topics. Okay, so this is the recent work about applying PCE methods on economic dispatch problem in power systems. So the economic dispatch problem, we're trying to minimize the operational cost by dispatching the traditional power generation unit while considering the randomness from the renewable generation. So this is a physical model, and the random inputs to the model will be the renewable generation, while the output of the model can be the cost or can be the dispatch solution. So in this study, we have carried out a numerical study in an integrated energy system where we have 118 bus system integrated with a 20-node gas system, where we have 120 random variables coming from 5 wind farms in 24 hours. And the data are directly from the Unreal website, Western Wind data set. And the total installed capacity of wind farm is about 12% of the total installed capacity. Again, so in first, we can see here that the data-driven sparse PCE methods can provide accurate estimation for the PDF and the CDF of the operational cost. Well, what is different compared to the last study is that the model response operational cost is kind of multi-model. It's far away from the Gaussian distribution. And it might be challenging for the PCE methods to build up the polynomial basis. But in this study, it turned out that the PCE method can still provide rather accurate estimations. And in terms of the efficiency, so in this study, the PCE method is approximately 33 times faster than the Monte Carlo simulations. Okay. And also in another work, we have studied the probabilistic power flow using another uncertainty quantification method called Low Rank Approximation method, which is has a better scalability compared to the PCE method because the coefficients of the low rank approximation model only grows linearly as the number of the random inputs increases. And we have apply this method and in the 1,354 bus power system where we have 713 random variables coming from 20 wind farm, 20 solar farms, and 673 loads. And we can see that for the power flow solutions, both the PCE and LRA, the low rank approximation, can provide accurate estimations for the PDF and CDF. Compared to Monte Carlo simulations. And more importantly, here we realize that if we just run a deterministic power flow, the deterministic solution is marked by the blue dashed line is well below the thermal limit. However, when we run the probabilistic power flow, it turned out that there are 40% probability that the branch power flow may violate the thermal limit. So this is another important result to demonstrate the impact of the uncertainty on power system daily operations. All right, so here are the conclusions and insights for my talk. So we have investigated the randomness from renewables on the power system security index. So particularly, we have realized that the transfer capability of the power system may have a considerable reduction, and the thermal limit may be violated with a high probability because of the randomness. And uncertainty quantification methods with fast speed and good accuracy are desirable to provide estimated probabilistic characteristics for this important system index and may help advance the development of probabilistic framework for power system security and stability assessment. And in the future, we are interested in developing uncertainty aware control and decision making. So as I said, we are interested in pinpoint the critical random variables, and then by controlling those critical random variables to enhance or maintain the security and stability of modern power system where we have a large high level of uncertainty. All right, so that's all my presentation. Thank you very much, and I will be happy to take any questions.